Okay, so hi everyone. My name is Melody Wu. I'm a third year biology major, chemistry minor, and my faculty mentor is Dr. Kevin Ko. And so today I will be presenting my work on expanding the scope of catalytic carbon hydrogen functionalization synthesis of medicinally relevant heterocycles. And so the background and inspiration behind my project revolves around the general theme of our lab, which is basically developing new chemistry to make biologically active molecules. An example of such molecules is 8-oxopalmitine, which has anti-gout properties, and we are able to form this molecule using new chemistry. And so 8-oxopalmitine is part of a group of molecules called protoberberines, which we propose can be formed from two smaller fragments via a direct carbon-carbon bond, which we see highlighted here in red. And so traditionally, this is done through an alpha arylation reaction where these two fragments are form a bond with each other, and we use a bromine here as sort of a leaving group. However, this can be pretty wasteful as bromine is a pretty heavy atom. And so in order to sort of lower the waste and contribute to green chemistry movement, we developed a new approach, selectively reacting at the desired CH bond by replacing this bromine with a hydrogen, which is the smallest and lightest atom on the periodic table. And thus we can minimize waste and also demonstrate the first direct alpha arylation at a carbon-hydrogen bond. And so this CH activation reaction is extremely versatile and high yielding as demonstrated by these molecules made by our past postdoc. And so since we've used this reaction to make biologically active molecules, we wanted to expand and use this chemistry to make underexplored heterocycles, which brings me to my project. And so my project uses this reaction to synthesize novel and also underexplored heterocycles with potentially biologically active properties. And so we're focusing on heterocycles since 60% of FDA-approved small molecule drugs contain fragments, heterocycle fragments. And so in addition, my project also expands the scope of green chemistry as mentioned previously, as I am decreasing chemical waste. And lastly, I'm also expanding the scope of CH activation reaction since it is typically done with electron poor substituents and I'm using electron rich substrates. And so the steps that I will be taking to gather information and analyze my data is to first gather information from literature on different conditions in which were successful information of product that is similar to my target molecules. Next, I will set up my reactions in an oxygen-free environment and work up the reaction in about 18 hours. I will then take an NMR of the crude reaction, which I will get into in the next slide. And after analyzing the NMR, I will determine if purification is needed. And if so, I will purify using a prep plate. And so after purification, I will verify that the sample is pure by taking another NMR, and then I would be calculating the yield of my reaction. And so mentioned in the previous slide, this is what an NMR looks like. This is specifically a proton NMR. NMR stands for nuclear magnetic resonance. And so each peak here represents a signal of a hydrogen on this molecule. And so this top NMR is the crude NMR and the one below is purified. And so notice how there are some peaks that are missing. This means that impurities that were in this crude reaction were removed via the purification process, and I can then use this molecule and apply it to my reactions. And so the purification process relies on silica gel to interact with various different products. And so this is what we call a prep plate, and it's sort of like electrophoresis for the biologists in the room. And so we can see the extent of separation via UV light. And so each band is actually a different portion of the sample. And by analyzing these bands, I can determine which ones actually contain the product that I need. And so moving forward, here are some key terms before I dive into the details of my project. And so the term heterocycle is a cyclic ring structure that has at least two different elements in its ring. And so here are some examples of protoberberines that have different substituents on its rings that fall under the category of heterocycles. And so the next term I'll be going over is an alkyne. An alkyne is a triple bond between two carbons. And so in organic chemistry, we don't really explicitly write out our carbons, but it is here for clarification purposes. And so the next term would be an enamide. An enamide is an alkyne with an amide group. And so as we saw in the previous definition, here is our alkyne in the molecule. And an amide group or an amide-like group is anything with like a nitrogen on it. And so anything nitrogen-like would fall under, with a carbon-carbon triple bond would fall under this term. And lastly, a brief explanation of the reaction that I used that I mentioned previously. So siege activation is basically when you're taking an unreactive carbon-hydrogen bond, which is here in red, and you bond it to a transition metal complex, which is this, we're using rhodium in this situation. And so by binding to this metal complex, you actually allow a direct formation of carbon-carbon bonds. So you're making something unreactive, reactive. And so diving into my research, my project started with this core reaction that is highlighted here, where we take a benzamide and we reacted with an enamide and form these two molecules on the right here. They're labeled major and minor product for convenience sake, but I will also be referring to them as the NH and NOMe product. And so with this reaction, I've been trying different metal salts. And so this is where the metal salt would be in my reaction condition. And so instead of silver acetate, I have tried a plethora of different silver salts, as well as copper, zinc, manganese, and cobalt salts. Additionally, I've also been swapping out different metal catalysts. So the metal catalyst up here is rhodium, and instead of rhodium, I've also tried different cobalt and palladium salts. And lastly, I've also switched out the solvents here. So instead of THF, I've used acetonitrile, DCE, TFE, and methanol in place to see if it will alter my yield, as my goal is to optimize conditions and get the highest yields for both products. And so my current progress, from some results from my current progress include, we started with this 2.2 equivalence of silver acetate. And so the term equivalence here just means like the ratio of the amount of silver that I'm using in relation to everything else that is involved in the reaction. And so with 2.2 equivalents of silver, we get about 30.5% major product and 2.74% minor product. We decided to play around with the equivalence of the salt. And so we tried 0.5 equivalent silver acetate, and that got us to about 19.2% major. So there was a drastic decrease, and there was actually no minor product formation. And so we decided to up the equivalence, and we do see an increase in both products with this increase. However, because the increase wasn't really drastic, we decided to keep it at 2.2 equivalents, as we also don't want to use too much metal in our reaction. And so following that, we replaced silver with copper, and that gave us about 4.26% NH product and 10.6% NOMe product. This condition actually gave us another very interesting molecule that ended up being becoming a target molecule of mine, which I will go into in the next few minutes. And so we also tried this reaction with zinc, and zinc actually gave us 83% yield of the NH product. And since this condition worked so well, we decided to try it with different benzamides. And so instead of this original NOMe benzamide, we fluorinated it, and that gave us about 56% NH product. We also tried it with an NO-PIV benzamide, and that gave us about 19.8% major. And so reverting back to our original benzamide, we also tried it with manganese acetate, and that gave us about 43.2% NH product. As I mentioned earlier, the copper acetate reaction actually gave us a very interesting product, which is this oxime product here. And so this product has actually never been made before, and this condition gave us about 22% yield. And so after playing around with several conditions, we actually found that by replacing copper with our original silver, as well as switching out THF for methanol, we arrive at about 52.4% yield for this oxime product. And so a summary of what I've mentioned so far, as well as future work. Through my chemistry, I'm able to make these 3 underexplored heterocycles, and these 2 on the right here have never been made before. These are the ideal conditions for each so far. And after correspondence with my PI, we've come to the conclusion that the highlighted molecules here, their conditions are basically sort of set in stone, and we're just looking into expanding the reaction. However, for the molecule in the middle, we're still figuring out what other conditions we could use to try try to increase this 10.6% yield. And so in the coming months, I will be doing a temperature study. Since these reactions are run at 50 degrees right now, I will be trying them at several other temperatures to see if that will also increase or decrease my yield. Additionally, we're looking to expand the scope of this reaction and see if it will work with different enamides and benzamides, as well as I've also been doing this reaction with enamides instead of enamides, so a double bond between the carbons instead of a triple bond. And so that would yield me these products that are similar to my target molecules here, just without the double bond. And so through my project, I have discovered a way to make underexplored heterocycles as well as novel molecules, including especially this oxime product here, which our collaborators at City of Hope, as well as agrochemical collaborators at such as Corteva, are interested in learning about the potential bioactive properties these molecules could exert. This project has shown great promise so far, and I am excited to see how it progresses. Thank you so much for your attention, and I will take any questions.
All right, great job. Looks like you've got a nice round of applause and celebrations there. Any questions for follow-up?
Yeah, hi Melody. The three molecules that you had there at the end of your slide, the benzamides, are those can those be used for scaffolds of any current like biological molecules that you know have activity?
So they don't really resemble, they just resemble fragments that are present in current, they do resemble current fragments that are seen in drugs that are on the market right now, but I don't know specifically these molecules just because a lot of them are very underexplored and some of them have never been made before, so we're not entirely sure on the properties of these molecules.
Gotcha. Okay, thanks.
Any other questions?
Do you happen to have any theory on why the zinc works so well at such a high yield?
I'm not entirely sure. I would probably consult more with Dr. Ko, and then I will let you know.
All right, well, thank you. Excellent job.